I just want to make a short video for us going from SPSS, doing an analysis of variance like we've done in some of the other videos, on our data that we have from Lomax and House-Vaughan from our Statistical Concepts textbook. If you're using the second course, that's the 4th edition from Lomax and House-Vaughan, then I'll be referring to chapter 1. If you're using the intro course, you just have to translate and be a smart person and know that that's 10 chapters later. It's the same chapter. The tables might just be table 11 instead of chapter 1. So the data comes from table 1.3, and we're going to conduct the regular analysis of variance for our one-factor analysis of variance for a fixed effects model, which I talk about in other videos. But in this video, I'm going to sort of try and decompose it into Excel, which I've already kind of copied and pasted in Excel. But first, I'm going to go ahead and calculate in SPSS for you. So under Analyze and under General Linear Model, I have univariate. We're going to do all of our univariate statistics for the general linear model with this module. Here's a dialog box that pops up. I already have number of statistics here. Let me go ahead and reset this. I can put number of statistics as our outcome measure. That is the labs. This is how many attendees there were, and level of attractiveness, as I talked about in other videos. This is what Lomax and House-Vaughan use for their grouping variable. And we have as options, we'll go ahead and get descriptive statistics just so we can see like raw score effect size, which is really just the difference between means. So I'll hit continue and I'll click OK. Alright, great. We have our descriptive statistics, which gives us our means and standard deviations for each level of our group. We have unattractive, slightly attractive, moderate attractive, and very attractive as our variable that separates out as our independent variable. That separates out what we're looking for an effect for. And then we have our outcome measure of number of stats labs. So we can see like unattractive here, only 11, number of attendance is 11 and on average. And for very attractive, 24.37. Our outcome here, I go into that in another video, but we have an F value. We care about the group effect, and we see that that F is significant. All I did was copy these two things and paste them into Excel, and here they are in Excel. So let's go ahead and break down some of the stuff we get out of our textbook. I'm going to be looking, starting off maybe on page 15 on table 1.4. I'm going to break up some of this stuff and also refer you back to page 29 of that textbook of chapter 1, which is really table 1.7, which is the outcome of between subjects effects, exactly what we have here. If you don't have the text in front of you, that's fine. The hope is for my students, you have it in front of you, but if you're not one of my students, you're just kind of listening in, that's fine. Just know that that text resource is out there for you. So when we talk about analysis of variance, we typically, one-way analysis of variance, we talk about between group difference, within group difference, and total difference. In SPSS, as maybe I've mentioned in other videos, we get our corrected model, which we're going to kind of ignore for now, and the intercept. The intercept, we don't really care right now about significance from 0, so we won't worry about that F value. We really just care about group, error, and corrected total. I'm going to go ahead and take those pieces, highlight them for you. I'll actually literally highlight them for you here. All right. And I'm going to change their names. This is not just group, this is like our between group. So I'm going to change it and say between group. I was right, between. Instead of calling it error, I'm going to call it within. And total is different here. Total is not the same as the total on page 15 on table 1.4. I know it gets confusing, but this is like the total degrees of freedom that are in your data. This is not n-1. This is n. The total pieces of information. This sums of squares is based on that as well. We're not going to be using that, so I am going to unhighlight that. what we're going to use is corrected total. This corrected total is our n minus 1 degrees of freedom. We have 32 people in our data set. We have n minus 1 is 31. We have 4 different groups. Number of groups minus 1 for a one-way analysis of variance is 3. And our within group variance, well, we know that, I guess previously in our chapter, if you see that we have within groups is going to be degrees of freedom is going to be n minus j, j being the number of groups. So within is n is number of people minus number of groups. So if we had 32 people minus 4 different groups, then we end up with 28. These two things, 3 and 28, should sum to the corrected total. And we see that that's true. I don't really need to do this, but just so maybe if it helps you later on, I'm going to add those two cells, and we see that we get the value of 31. It's one of the checks we can do it. As you go through some of your assignments and practice on understanding this table, our analysis of variance table, this can be very helpful to know how degrees of freedom should break out. So if I gave you any 2 of the degrees of freedom for between, within, and corrected total for a one-way analysis of variance, if I give you any 2 of those, you should be able to answer the third one. So if I told you corrected total was 31, and within groups source of variance was degrees of freedom was 28, you should know that the last between group should sum to 3. All right, so let's go through some other things that are helpful in this table. We have sums of squares. In class. We'll go through how to calculate these by hand, like if we were on a desert island or something, but instead for now we have the computer calculating it for us. So let's just go through a couple of those and see that they add together as well. We can see that the between group sums of squares, I'll go ahead and add that. I'll take between groups, that's 738, and add that to our within group variance, and we see that it sums to that same value of 1749. See, 1749. So again, if we were given any 2 of our sums of squares, we should be able to calculate the third one. If I told you that we had 1749 as our corrected total and 738 as the between, we know that we must have 111 for our type 3 sums of squares for within group, our within group variance. So I will say now that's for the one-way factor analysis, and for most of our models, for fixed effects models, we'll see that that's true, that these things always are going to sum up well. But as we get further down the road, there'll be some issues that come up that this won't sum up perfectly. But that's okay. We'll have a rule system for that as well. So other things that we do with this table is we take and we get our mean squares. So our mean squares is just like a variance estimate. Matter of fact, I think of mean squares as a variance estimate, and we'll see in the class and in other videos how we discuss that. But basically, we're taking a numerator. We get the sums of squares, which is just like the numerator of a variance model, and we take the relative denominator. In this case, for between group, we would take 738 and 3 and divide, so that would be 738 approximately divided by the appropriate degrees of freedom. Appropriate just going across that column. You can see I'm going across, and I get 246. Well, lo and behold, no surprise to you, 246 is your mean square. Think of that as the variance that's related to the between group variance. And we can think below. We can just take the same thing. Matter of fact, I can just kind of drag and drop to show you that we just take the value of 1011 divided by 28, and we get 36. We can just go across. So now we have the variance related to being between the two groups and the variance for within a group. So the variance within a group is also our error variance. That's how much variation we just expect to occur, right? Given the type of data that we have, it's not surprising that our variance is 36. If we took the square root of that, we can see that we'd have standard deviations that would be really similar to a value of 6. If you took the square root of 36, you'd end up with 6, and these are all pretty close to that total. If we take the numerator of between group source of variance and our denominator is within, I'll go ahead and do that right here. We take our numerator, and I'll do it on our data that we just created. We take 246 and divide it by 36. We get 6.8. That is our F value. And we could go look that up on the back of the text. Or, even better, you guys could use Google and go look up the ratio of, if you have degrees of freedom in your numerator of 3 and degrees of freedom in your denominator of 28. You have access to it because you guys can go Google or use Yahoo search or Microsoft search engine online, go find an F table and see whether it's significant. Of course, since we did an SPSS, it already gives us our significance value of 0.001. I'm going to do a couple other things with this data set, 'cause we're decomposing this a bit, so this will also help with homework assignments. You know, so you kind of got to feel that you could fill in the blanks here, right? If this piece were missing, this 3 were missing, you'd be able to fill in the blank. If the mean square was missing, if both those mean squares were missing and you had this information here, you could calculate out both of those mean squares. And in some of our assignments, we do some of that. So this is just also some help if you need some help with some of those assignments for trying to understand the analysis of variance table, then this would be a helpful video to watch. So for example, your computational problems, if you went to computational problem 1 in your textbook, you'd be able to see that on page 49 of your textbook, you'd be able to see that this kind of is what we're doing. We're going through and we're going to complete the analysis of variance summary table, and I'm kind of giving you those tools to do that. Well, I try to keep these lectures sort of shorter and manageable, but there's a couple other things I want to do, so you can always hit pause instead if this gets too long for you to listen to and come back to it. But I want to just go over eta squared real quick. Eta squared is one of our basic effect sizes that we can get out of SPSS. It's a very simple, for the one-way fixed effects analysis of variance, it's a very simple model. It's just the ratio of between group sums of squares to sums of squares total. So I can take, without even going into SPSS and asking for that calculation, I can take our between group sums of squares, which is 738. I'm going to do that just over here. I'm going to take that 738, I'm going to divide it by the corrected total, and I get a value of 0.422. You can see on your textbook that is also correct on page 16. But also, let's just go in SPSS real quick and ask for that so we can see what it gives us for our effect size. I'm going to go back in, rerun our general linear model, and under options, now I'm going to click effect size. I'm going to turn off descriptive statistics, and I'm going to click OK. Look at that. We got our group. We go across. We can see that the partial eta squared, in this case it's eta squared, for our whole model is 0.422, yet we did it with our table here in Excel based on just having the outcome analysis of variance table. When we think of effect sizes, that's kind of a standardized effect sizes. So we're taking the variance around between group variance, which is as a sums of squares, and the total sums of squares, and we're saying how much of between group sums of squares is total sums of squares, and that's really what the ratio is. The math is just slightly different for omega squared, and F just is an adjustment on this. I'm not going to go over that now in this video. We'll do that some in class, or maybe I'll make another video or say it in another video later. But effect size, what the heck is effect size? The simplest way to think about effect size to me is just think about the differences in the mean. The raw score effect size can be something as simple as, what is the difference in the mean of group 1 and the mean of group 2? So if I take, let's just go ahead and do it this way. I'll go the opposite direction. That is, maybe that's intuitive. I'm going to go the mean of group 2 minus the mean of group 1, just so I get a positive value. And I see the difference is 6.75. Well, it's not standardized. I'm not even going to bother standardizing it. But what that tells me from a practical perspective, as a practical effect size, is that when I go from group 1 unattractive to group 2 slightly attractive, there's an increase of a raw score on average of 6.75 in the number of classes someone attends. that may or may not be meaningful. If I'm a subject matter expert, or if I'm someone that is trying to get people into these number of stats support classes, then that's a very important number for me, that raw score. Now we'll do another extreme. How about we do group 4 minus group, instead of group 1, because that's going to be pretty big, we'll do group 4 minus group 2, and we'll see that's 6.5. So as we shift up even further down, we get another increase of 6.5. And we could do the others as well. We could say here's group 3 minus group 1, and here's group, well, that's actually slightly, we'll do, I'll go back and do this minus group 1, so we'll use group 1 as a reference for all of them. That's all 3. So, and you can see basically by what I did before, we can do the difference between group 1 and group 2, group 2 and group 3, group 3 and group 4, or we can do all of them to this same baseline group. But this is the beginning of understanding an effect size. The raw score mean is like a raw score effect size. We know we're getting a feel for how large of a difference there is, and if it's a practical difference for us. One other thing I just want to say about our data we already have here, we have an R squared, and that R squared is a measure of how much variance in between group variance is relative to our total variance, which sounds really familiar. It sounds like eta, and that's because it basically is. It's the same calculation. We're taking sums of squares between divided by sums of squares total, and this becomes the simple bivariate Pearson correlation, which is our R squared value. So it's kind of like, how much of an effect do we have? It's another effect size measure, and it's directly, in this case, related to eta. So these are just an example of some of the decompositions. I just took, as you saw, our data out of SPSS and tried to demystify some of these tables so that as you're doing your assignments, or even maybe if you're not in this class, or if you're in this class and you're coming back to this later, that you get an idea of what are some of these components of the analysis of variance table and how they relate. Given the amount of time on this one, I'm going to go ahead and cut it now, and maybe make later on down the road some more of these type of videos that kind of deconstruct some of what's going on in the table.